Hello students, today we will learn about the different types of oscillators. Different types of oscillators. So mainly there are three types of oscillators. LC oscillators. L means inductor and C means capacitor. So LC oscillator. Then second is RC oscillator and third is crystal oscillator. So these are the main three different types of oscillators. LC oscillator, in LC oscillators there are few coils and trimmers or capacitors which are connected in parallel to form LC circuit or tank circuit. So tank circuit is formed by using inductor and by using variable capacitor, or by using variable inductor or variable capacitors. So tank circuits are used in LC circuits to form oscillations. So this is the first type, LC oscillator. Second is RC oscillator. In RC oscillators, resistors and capacitors are used. And third is crystal oscillator. So these are the main three types of oscillators. So we know that oscillator generates or oscillates various types of signals or waveforms with different frequencies. Okay, the frequencies of oscillators can be varied by either varying capacitor or either varying inductor. Okay, or either varying capacitors. The frequency of oscillations are generated in oscillators. So there is no need of any AC input signal for oscillators. It itself generates the oscillations. Okay. Also in crystal oscillator, there is one crystal and it vibrates, and due to these vibrations, oscillations are produced. So first we will study about LC oscillator. So in LC oscillator there are two types of LC oscillator. First is a Hartley oscillator and second is Colpitts oscillator. So today we will learn about Hartley oscillator and Colpitts oscillator, how it generates oscillations, or how it produces waveforms, AC waveforms with various frequencies. So first we will study about Hartley oscillator. So in Hartley oscillator there is one transistor. It is used as an amplifier. Then there are two resistors R1 and R2 which provides a bias for transistors. That is, the base emitter junction of transistor will be forward bias and base collector junction will be reverse bias. So these R1, R2, RE, these are the biasing resistors. These resistors provide necessary bias for this transistor to operate it. Okay, these resistors provide necessary bias for the transistors. Then there is a RF coil. To produce oscillations, and it opposes a change in current, and it opposes a change in current, or it isolates the DC from AC. Therefore, this RF coil is used. Then there are two inductors, L1 and L2, to produce oscillations. Across this inductor there is one variable capacitor to form a tank circuit. So this tank circuit produces oscillations. Okay, tank circuit produces oscillations, and the frequency of these oscillations can be this frequency of oscillations depends upon the value of capacitance or value of inductors L1 and L2. The frequency is given by the equation 1 upon 2 pi root L1 plus L2 into C. Okay. So first we will study about these Hartley oscillators, R1 and R2, RE. What are the functions of R1, R2 and RE? This R1, R2, RE. These provides necessary bias for the transistors. These are the functions of these three components R1, R2, RE, which are used in Hartley oscillators. R1, R2, RE. These provides necessary bias for the transistor to operate it. What is the operating condition of transistor? It's best to operate the transistor as an amplifier. To operate the transistor as an amplifier, we know that there are two PN junctions in transistor. So emitter to base one PN junction and base to collector another PN junction. So first PN junction, that is emitter to base, it should be forward bias, and base to collector, this junction should be reverse bias, so that the transistor operates and it will act as an amplifier. So for this purpose, this R1, R2, RE, these resistors provide the necessary bias for this transistor. Okay. Now there is one capacitor C2. This capacitor C2, it is a blocking capacitor. It is called as a blocking capacitor. It blocks DC. It opposes DC, and it passes the frequency of oscillations. It passes the signal. The signal is passed through this capacitor, and it is given to the tank circuit. It is given to the tank circuit. So C2 is a capacitor for blocking DC, and it provides path for AC current. It provides path for the AC current or alternating current to the tank circuit. This C2 passes AC and it blocks DC. So this is called as a blocking capacitor. It does not allow to pass DC through it. It only passes AC or alternating current to the tank circuit. Okay. Then RFC means a radio frequency coil. Radio frequency coil or choke. It is also called as a choke, RF choke or a radio frequency coil with a large reactance. Okay. Its inductive reactance is very large, and it is used for oscillating the frequency, and it prevents or it opposes RF current from reaching the DC source that supplies to the collector. Okay. Then R1 and R2 provide self bias voltage, thus making the amplification of the input voltage large. Okay. This for producing large signal, that is the input signal which is fed from this tank circuit to the C1. So this input signal is made large with amplification of this transistor. That means its strength of the signal is increased by this transistor, and therefore this transistor is used as an amplifier, and it makes the input signal large by making amplification of the input voltage. Thus transistor is operated in a class C condition. That is, we know that there are three types of amplifiers: class A amplifier, class B amplifier, and class C amplifier. So this transistor is operated in class C mode. That is, in class C amplifier, it is used as a class C amplifier. So in class C amplifier, the efficiency of transistor is very large. So maximum power of the signal is obtained in the tank circuit. Okay. So first we will study the circuit operation of this Hartley oscillator. So when VCC is switched on, that is when supply is given to the circuit, and when this VCC is switched on, then a transient current is produced in the tank circuit, and this tank circuit consists of L1 and L2, which are in series, and variable capacitor. It is connected across this inductor. Therefore damped harmonic oscillations are produced by this tank circuit. Damped oscillations are produce. The oscillatory current in the tank circuit produces uh, the oscillatory current in the tank circuit produces corresponding oscillatory voltage between the points A and B. Oscillation, that is AC voltage, is formed across the points A and B and across L3. Okay, then as their midpoint is Earth, okay, the midpoint of L1 and L2 is Earth, therefore Y is at zero potential. This point Y, it is at zero potential, and thus the X is negative and Z is positive. This is the X point and this is Z point. So this X will be negative and Z will be positive. This is Z point and this is X point. Okay, so this X is Z is negative and this X point becomes positive and Z point becomes negative. Okay, Z point becomes positive and X point becomes negative, and hence there is a phase difference of 180 degree. That is, the AC voltage obtained across L1 and the AC signal obtained across L2, these are in out of phase. These two signals, the AC across L1 and AC across L2, these are 180 degree out of phase, and therefore the voltage across L2, this voltage across L2 is then fed back to the base of this transistor. It is called as a feedback path. It is called as feedback path. So voltage across L2, it is fed back to the base of this transistor through C1. C1 is a coupling capacitor. So it passes this feedback signal to the base of this transistor. Okay, and L1 has the output voltage. L1 has the output voltage, and it induces into the coil L3. Okay. Hence, the parallel resonance circuit, this is also called as this tank circuit, it is also called as a parallel resonance circuit. It is also called as parallel resonance circuit, which provides 180 degree phase difference between the voltage feedback to the base and output collector voltage. This output collector voltage and this feedback voltage, these are 180 degree out of phase. So we know that to produce oscillations, there must be total 360 degree phase shift. There must be total 360 degree phase shift. So this transistor amplifier provides 180 degree phase shift, and this LC circuit or tank circuit, it also provides 180 degree. So this signal is totally, there is a 360 degree phase shift, and therefore oscillations are produced. Okay, then the common emitter amplifier, this is a common emitter amplifier. So this common emitter amplifier produces 180 degree phase difference between input and output voltage, and thus the total phase difference is equal to 360 degree, that is 0 degree, and thus satisfying the conditions for oscillations. Thus that means the conditions of oscillations are satisfied, and therefore oscillations are produced. If the loop gain, that is beta AV, if the loop gain of the amplifier is greater than 1, that is, if A beta or beta AV, if it is greater than 1, beta AV or beta AV, if it is greater than 1, then we get sustained oscillations. Okay, then we get continuous oscillations or sustained oscillations if A beta is greater than 1, and thus the frequency of oscillations, it is given by the equation F is equal to 1 upon 2 pi root L1 plus L2 into C. This is the formula for the frequency of frequency in Hartley oscillator. that is F is equal to 1 upon 2 pi under root L1 plus L2 into C. Because L1 and L2 these are in series, therefore 1 F is equal to 1 upon 2 pi under root L1 plus L2 into C. This is the formula for frequency. Now what are the advantages in Hartley oscillator? So first advantage, it is instead of two separate inductors, only a single coil can be used, and at any desired point on the coil is grounded, and thus two coils are then formed. Okay. Then second, the frequency of oscillations may be varied. This frequency of oscillations can be varied by varying this C, varying the capacitance C, because this is a variable capacitor. So by varying C, different frequencies are obtained. Okay, or this frequency of oscillations can be varied by using variable capacitor. By using this variable capacitor, the frequency of oscillations can be varied. That is, for suppose for 1 kilohertz or 1.5 kilohertz. In this way, if C is varied, if this C is varied, then frequency of oscillations can be changed. The frequency can be changed by varying this C. Okay. Then third, Hartley oscillator may be used as, it can be used as a local oscillator in radio receivers. It can be used as a local oscillator in a radio receiver to provide the RF output. Okay, so this is about Hartley oscillator. Then we will study about Colpitts oscillator. Okay, so this is the circuit diagram of Colpitts oscillator. So in Colpitts oscillator, the circuit diagram of Hartley oscillator and Colpitts oscillator are same, except here the two capacitors are connected in series instead of two inductors. As in Hartley oscillator, the inductors are connected in series, and in Colpitts oscillator, the two capacitors are connected in series and its center point is earth. Here the inductors L1 and L2 are connected in series and their center point is earth, and here the capacitors C1 and C2 are connected in series and their center point is earth. Only this is the difference between Hartley oscillator and Colpitts oscillator. Then both circuits are same. Okay. Also here in this output circuit, tank circuit is used. Here also in the output circuit, this tank circuit is used to form damped oscillations. So first of all, we will see the functions of each component used in Colpitts oscillator. So here resistors R1, R2 or RE, these resistors provide a necessary bias for the circuit. The frequency of oscillations is it is determined by the capacitors C1 and C2. These components C1, C2 or L, these components determine the frequency of oscillations. That is, the frequency depends upon the values of this C1, C2 and L. Okay. And these C1, C2 are connected in series, and these capacitors are then connected in parallel with the inductor L to form a parallel resonant circuit. Okay. The function of C4 is to block DC. The C4 blocks DC, or it opposes DC, and it provides AC path from collector. It provides AC path from collector to the tank circuit. Okay. Then RFC is a radio frequency coil or choke, and with large reactance. And this RF currents, this inductor prevents the RF current from passing through the source of supply VCC of the collector voltage. Okay, it also prevents short circuit of alternating output voltage. It also prevents short circuit of alternating output voltage. That means it does not it opposes short of AC to the ground. It opposes uh, short circuit of AC to the ground. That means when the transistor is in conducting state, then the AC current flows, and this AC current, it is passed through capacitor, and it does not pass to the ground. So this RF coil, it prevents AC from passing through it to the ground. It opposes AC from passing to the ground. That is, it prevents AC. It prevents AC, or it prevents short circuit for AC. It prevents short circuit from AC, and this AC is passed from collector to the tank circuit through capacitor C4. This is a DC blocking capacitor. It opposes DC, and it passes only AC. This AC signal is passed through capacitor C4 to the tank circuit or parallel resonant circuit. Okay, then R2, C3 and R2 give necessary self bias voltage, helping the transistor to operate under class C conditions. C3 and R2 give necessary self bias. C3 and R2. This C3 and R2, this provides C3 and R2. This provides C3 and R2 provides necessary self bias voltage to the transistor, and thus this helps the transistor to operate under class C conditions. Okay, now we will see the working of this Colpitts oscillator. So when collector supply is switched on, or when VCC is switched on, then transient current is produced. The transient current is produced in the tank circuit. Transient current is produced in the tank circuit, and this provides input signal to the this provides the input signal to the base of transistor. This provides, and since transient current is produced in the tank circuit, then this resonant circuit provides a signal to the base of transistor, and this the oscillatory circuit, this oscillatory current, the oscillatory current or AC current, then in the tank circuit produces AC voltage across capacitor C1. It is output capacitor C1, and another voltage across C2. Okay, and the voltage across C2 is considered as input voltage, and voltage across capacitor, it is considered as output voltage. So these voltages have a phase difference of 180 degree. The voltage across the capacitor and voltage across the capacitor C2, voltage across the capacitor C1 and voltage across the capacitor C2, these voltages are exactly 180 degree out of phase. Okay, and this transistor is also, it produces 180 degree phase shift of the signal. Thus total 360 degree phase shift or 0 degree phase shift is obtained to produce oscillations. Okay, the voltage across the C2, it is fed to the base of the transistor. This voltage across the capacitor C2, it is fed back to the base of this transistor. Voltage across the capacitor C2, it is fed back to the base of the transistor, that is to the input terminal. The common emitter amplifier provides another phase shift of this common emitter amplifier, that is transistor. It provides 180 degree phase shift. It provides phase shift of 180 degree between the input voltage and output voltage. Thus the total phase shift is 360 degree or 0 degree. Now if the loop gain A beta of the amplifier is greater than 1, if this loop gain A beta, it is greater than 1, then sustained oscillations are produced. or continuous oscillations are produced. Okay. Then this frequency of oscillations. The frequency of oscillations in Colpitts oscillator, it is given by the equation F is equal to 1 upon 2 pi under root L C equivalent. 1 upon 2 pi under root L C equivalent, where C equivalent is equal to, because these capacitors C1 and C2 are connected in series. So when the capacitors C1 and C2 are in series, then its effective capacitor or its equivalent capacitor is given by C1 into C2 divided by C1 plus C2. Because these capacitors are in series, therefore the formula becomes F is equal to 1 upon 2 pi root L 2 pi under root L C equivalent, where C equivalent is equal to C1 into C2 divided by C1 plus C2. Okay, so in this way we have studied these two oscillators, LC oscillators, that is Hartley oscillator and Colpitts oscillator. So we will stop here.